Hello everyone, editing Saif here. I just wanted to record a little thing to tell everybody that this live recording was recorded before the the offline recording of part one, which was a retake of the original live part one. So I'm going to be referencing some things from the live session of part one that aren't going to be in the actual final recording, final video that's on YouTube, just so that everything makes sense. And another thing that I wanted to clarify is that in this recording, I hadn't switched over yet from using omega of xy to f nabla of xy. So there's going to be a little bit of a continuity thing going on there. I realized after recording this that these two are actually the same. They're both two forms. I had originally mistakenly thought of them as being two different types of objects, but no, even though this is a rank 2 tensor, it's actually a 0-2 tensor, right? So they're both two forms. So hopefully that clarifies that we're still going to be using omega in this recording. And so that's all. I'll hand it back over to the live recording to get started. Hello, welcome back everyone to Complex Differential Geometry. We're doing part 2 of Connections, Curvature, and Chern classes. I renamed the section, this lecture midway, because I thought this is a more descriptive name for what we're doing. They're all connected. Curvature is connected to connections, and you get Chern classes from the curvature, so it's all topical, but it describes what we're doing. So before we get back into what we were doing, let's do a little recap. So what were we doing last time? We started off talking about connections. So we defined something called a connection. And this was a map, nabla, that took us from the smooth sections on E, so E is a vector bundle, So it took us from smooth sections on E to smooth sections on E tensored with the cotangent bundle, which is pretty much the same as saying smooth sections on E tensored with smooth one forms or differential one forms. So the way we were reading this is that it's a one form where at each point its coefficient is a vector. So overall, you get a coefficient over the entire manifold since you have a vector at each point, and it's by definition smooth because this has to be a smooth map. Smooth. So therefore, this is a vector field. So what is this? You can think of this as a universal directional derivative. If you give it a vector field, it'll give you the rate of change in every direction for every vector on the manifold. That's a lot of information, but that's what this output is storing. And then we define from that, well, we looked at some properties. I'm not going to go over the properties again, but we also defined something called the covariant derivative. The idea for the covariant derivative came from the fact that with this is just a machine. Remember, this is a one form. So this is a one form. And what we said about one forms is that a one form will give you a directional derivative once you give it a vector field to take the directional derivative along. And then you give it a point, and then it'll give you the derivative at that point, and so forth. So if we give it a vector field, let's say the vector field's name is x, we get something called the covariant derivative. This is a map that goes from gamma e, so smooth sections on e. You can say that they're e vector fields also. Let me write that out. E vector fields. I don't know if this is an official term, but yeah. So as opposed to vector fields from the tangent space, this is, since E is is an arbitrary vector bundle with an arbitrary vector space as its fiber. This is some other kind of vector field, and it'll return you another vector field, right? So this is where this x has consumed this one form. So like again, you have that one form plus a vector field. And remember, one form is just the official name that's been given to a covector field, right? So a vector field and a covector field together, they annihilate each other. That's the way I think about it. And so that extra omega 1m disappears from here. So you just get the vector field. So that's what the covariant derivative gives us. And then, so this covariant derivative, you can think of it as the derivative that is more intrinsic to the manifold, because the way we thought about it, the way we arrived at the covariant derivative, was we thought, okay, well, I have this manifold. I would like to kind of differentiate vector fields on this manifold by thinking of the rate of change of the assigned vectors at different points. But these 2 points are, let's say they're P and Q, they have 2 different tangent spaces, TPM and TQM. In fact, they don't actually have to be tangent spaces, so I misspoke last time. They just have to be vector spaces. So this in general can be EP, and this can be EQ. It applies to tangent spaces, but it applies more generally to any fiber. And so these are the fibers, but the problem is the same. You have vectors that live in 2 different vector spaces, which are essentially 2 different universes. And how do we connect those? Well, we connect them using the connection, and then a specific restriction of the connection gives us the covariant derivative. So you can think of the covariant derivative as this like more intrinsic definition, or more true definition of what a derivative should be on a manifold. And so then we looked at some of the properties of the connection, and something that I didn't emphasize enough last time is that the properties of the connection that we looked at, properties of the connection, they were really to show that nabla does behave like a derivative. So first of all, that nabla of 0 is 0. That's something that's one of the things that you expect a derivative to do, right? Like d dx of 0 is 0. Number 2 is locality. So if we restrict the connection to be acting on a local section, then if these two are the, okay, so if the restrictions of the local section are the same, S1 restricted to U is equal to S2 restricted to U, then that implies that nabla of S1 restricted to U is equal to nabla of S2 restricted to U. And then number 3 is C infinity linearity. in X, in this, where'd it go? In this input. So you can think of the connection as having two inputs, X and S, right? So this is the gamma E input, and this is always going to be a gamma TPM input or gamma TM input, right? So this is, you could, I tend to call this the flow vector field. It's the vector field along which we are differentiating. So what this is basically saying is that it has C infinity linearity in this first input. And this is what implies that the nabla is defined pointwise. Defined pointwise. So each the derivative at each point only depends on the vectors in that point and around that point. So or it only depends on the vector at that point, and it only depends on information on the manifold near that point. That's what the locality is telling you. So these three properties, I'm not going to prove it here, but this is enough to make nabla a derivative operator. Or I think it's better called a differential operator. That was the significance of these properties. We're going to do something I don't usually do, which is go to the next page in order to finish the recap. So then we looked at affine connections. Affine connections are connections where E is equal to TPM, or sorry, E is equal to TM. And so this is on the tangent bundle. And there are some extra things that we can define on affine connections. The main one being torsion. Torsion, T of xy is equal to nabla xy minus nabla yx minus x, the Lie bracket of x and y. And maybe I forgot to talk about this last time. So if T of xy is equal to 0, we get a very special kind of manifold called a torsionless manifold. Or sorry, we get a very special kind of connection called a torsionless connection. Torsionless connection. So this is going to become important in the next few lectures. That's why we mentioned affine connections. And if a manifold admits an affine connection, it's called an affinely connected manifold. Okay. So then we looked at, we looked at holomorphic vector bundles and we looked at holomorphic sections, but we're going to redo that because I'm going to scrap that recording. But what we would have looked at is local frame fields. So these are bases for entire vector fields. So they allow us to decompose vector fields into components. These are called local frame fields. I believe local frame field is a more archaic word for them, used by Chern, Chen, and Lam. I think nowadays they're just called local frames. I'm not sure though. So, but yeah, I hear them being called local frames as well. I think that's more true to what we call them in physics, which is like local reference frames or something like that. That's mainly motivated by general relativity. Okay, so we looked at local frame fields, which were sections of, they were sections of the frame bundle, but they were also collections of uh, there are collections of local sections. So E alpha is a map from U, which is a subset of M, to E, uh, where pi after oh, there's a little typo over here. I wrote S the last time. I have to change that. Pi after E alpha is equal to the identity. And, 1 less than alpha less than Q for a Q-dimensional vector bundle. And then we looked at, so now we use the basis to do this decomposition. So we define the connection coefficients. So that was like we took nabla of E alpha, and we said that, well, let's let this equal to omega alpha beta tensor E beta, which we also sometimes equivalently write as omega alpha beta E beta. So here, the important thing to remember is that these are not tensor indices, not tensor indices. They are matrix indices. So they're literally, so each of these omega alpha betas are, each component, each element in the matrix is a one form, and um, and then you have a matrix of these one forms. So that's what each of these alpha betas are indexing. So just keeping that in mind. And then this is from, right, so like this, you can kind of think of this as like, this is the part that's from omega 1 m, right? And then this is the part that's coming from gamma of E. So that's kind of how you can think about it. But then the coefficient of this is kind of being absorbed into that form as its component. So now that we have connection coefficients, then we define the curvature form and the curvature tensor. So the curvature tensor was F nabla, which is equal of xy, which was using the connection in the two different orders. Am I getting that right? Yes, that is the order. So nabla x nabla y minus nabla y nabla x minus nabla of the commutator, or the Lie bracket, I keep calling it the commutator, the Lie bracket of x and y. So, and then this term accounts for the fact that x and y themselves might not commute with each other. So we subtract that off. And then we show that this is equivalent to this curvature 2 form omega. Omega of xy is equal to d omega minus omega wedge omega of xy. This is since small omega was a one form, and here we have the exterior derivative of omega. So, and this is also, these are both two forms, as they would have to be since they're being subtracted off of each other. So these are both two forms. So then we know that this is a two form. Okay, so small interjection here. I didn't explain correctly why omega is a two form. Omega is equal to d omega minus omega wedge omega. I mean, this is revision, but let me make it clear. This is a two form because omega, as we know, is a one form. One form. And so therefore its exterior derivative is a two form. And since this is a one form, the exterior product of two one forms is also a two form. So then we get a pure two form. I incorrectly said that a two form, since they're being subtracted off of each other, they have to both be two forms. That's not true. We could be in the tensor algebra, and in that case, one of them could be a two form and the other one could be any other form. And so then we would have a mixed grade element. But since they're both two forms, therefore omega overall is a two form. That's the actual explanation. The last thing that we looked at was endomorphism valued forms, which they're just matrix. They're the same thing as matrix valued forms, so forms whose coefficients are matrices, but the matrices in this case have a very special transformation property which makes them endomorphisms, which is that omega is equal, omega prime, let's say, is equal to a dot omega dot a inverse. This is what makes it an endomorphism valued form as opposed to, sorry, endomorphism valued form, as opposed to just a regular plain matrix valued form. And this is also a generalization of tensor valued forms. So for it to be a tensor valued form in the way that we define the tensor, E would have to be the tangent bundle. So on the affine connection, this would be a tensor valued form. But in general, E is not the tangent bundle, and therefore we have to call it something a little bit more general, the endomorphisms on E, which is a linear map L from E to E, which is a matrix that takes vectors on E to vectors in E. Yeah, so then we did some calculations. I couldn't do the working for the calculations last time, but I have since written out the calculations, and they are now in the appendix of the lecture notes. And hopefully I will be putting in some more calculations in the appendix. One of the reasons why I was going back and forth on doing the calculations in the first place, the calculations would destroy the pacing of the notes, and so we would get stalled for a long time trying to figure out how to solve something. I think the adding an appendix actually is a good way of diverting all of that to another place where it's not necessary for the overall narrative that's being built, but if you really want to see, if it's unsatisfying to just see the result, then you can go and look at the calculation. Right. So that was a pretty long recap. We're at the 20-minute mark now, but now we can talk about what we're going to talk about today, which is connections on complex vector bundles. So let me write that out. Connections on complex BBs. Don't feel like writing it all out. So we know that with real vector bundles, our connections had to be R linear, right? So let me write out our linearity. It was nabla of A S1 plus B S2. That had to equal A nabla S1, put a parenthesis there, plus B nabla S2. Keep forgetting the parentheses. So we were saying before that A and B had to be elements of R, and now we're just going to upgrade this to C linearity, which is that A and B have to be elements of C. Specifically, that means that I is now a possible number that we can put in as a coefficient, right? And then we have the Leibniz rule we get the same Leibniz rule as what we had before, where nabla of fs is equal to nabla of f times s plus f times nabla of s, or f nabla of s, right? And so then if we can actually use these two rules, and if we combine them, especially for the C linear case, let me write that out, C linear. If we combine C linearity with the Leibniz rule, what do we get? So let's say that f is equal to, let's specifically look at the case where f is equal to I. Then this will turn into nabla of is is equal to nabla of I tensor product s plus f nabla, oh, I keep saying f, so I nabla of s. So we can interpret this in a few ways. So first things first, this is 0 because I is a constant, so it doesn't have any derivative. You have to think of this as like a constant function over the manifold. So this is constant. And the rest of it, so here we have S, which is a section, right? So we know that J of S is equal to IS. We didn't look at this specifically for vector fields, but this is an extension of the idea of J on each of the vector spaces in the vector bundle, right? So the idea is very similar. So we can say that this is J of S. And here we have to be a little careful. We have to extend J because J actually takes a vector field, right? But this is not a vector field. This value here is an omega 1m times, tensor producted with a vector field, right? So we have to be careful there. So we have to extend J to take something like this, and all we have to do is we have to make sure that J passes through this first thing and just applies itself onto the section. So if we had J of alpha tensor V, then that would have to equal alpha tensor J of V. If we extend it this way, then it's well defined, and therefore we can say that this is J of nabla of S. So if we kind of put all of that together, what we get? The middle term vanishes, and we've rewrote the two terms on the two sides. So we get nabla of J of S is equal to J of nabla of S, which means that these two together essentially mean that nabla and J commute as operators. Commute. That is the upshot of what any complex connection has to do, is that it needs to make sure that nabla commutes with the complex structure. And you can think of this commutation, maybe I haven't referenced this idea before, but you can think of this commutation as the idea that one structure must not break the other structure. If applying nabla and then applying J broke the complex structure of the manifold, then J would not have the same effect if you applied it after nabla, and vice versa. So J cannot ruin the nabla's connection structure, and the connection cannot ruin the J structure. And therefore, this is the way that the compatibility manifests for that reason. This is how we expected it to work. Sorry, I forgot a parenthesis here. So we have here an additional problem. So complex compatibility is all well and good, right? We have another problem, though, which is that we introduced these things called holomorphic vector bundles. Holomorphic vector bundles. So what are holomorphic vector bundles? To quickly recap, if when we had these local trivializations, let's say that I have this open set U, and I'm thinking of the fibers that are twisting around and coming out of this U. So this is E restricted to U, and we had this map. Well, if we call this U alpha, then I can call this phi alpha. That mapped us to the local trivialization, or you can call the map the local trivialization, where the fibers were straightened out, right? So this was U alpha, and this was CQ, and which meant, sorry, I'm supposed to put the Q's at the bottom. So that meant that this whole structure was a U alpha Cartesian product with a CQ, right? You can call the end product a local trivialization, or you can call this the local trivialization. They're also called bundle homomorphisms, I think. So we use these phi alphas. The upshot is that we use these phi alphas to create these transition maps. G alpha beta would be equal to phi alpha inverse after phi beta. And as I said before, maybe I've gotten the alpha and the beta mixed up in this definition, but if I did just flip them, maybe it's phi beta inverse phi alpha. But the underlying problem is still the same, which is if I have two intersecting open sets, U alpha and U beta, let's say this is U alpha and this is U beta, I might have the same point in the middle, right? This is U, this is P, let's say, and there's a fiber for both of the local trivialization. So there's a fiber EP alpha, and there's a fiber EP beta. And in order for something to be a holomorphic vector bundle, our holomorphic coordinates have to be well defined. So if on one local trivialization they're one way, and on the other local trivialization they're in an incompatible way, we can't have that. What will make sure that they're not incompatible is that these transition maps, which are essentially what takes us between these two, is holomorphic. So that's the condition for being a holomorphic vector bundle. And that makes our complex analysis on this vector bundle well defined. And we would, just like we said with the last one, that nabla and J had to be compatible with each other, nabla also has to be compatible with these holomorphic transition maps. And so the next thing that we're going to do is we're going to see how we can make the connection holomorphic compatible with the holomorphic structure. So with all that ado, so a holomorphic section, so we basically already defined a holomorphic vector bundle in that explanation. It's just that its transition maps are holomorphic. So then if we want to define a holomorphic section, we just define a regular section S that goes from U subset of M to E, subject to the constraint pi after S is equal to the identity on U. This condition will restrict us to assigning. So if we have this being U, and we have a point on it P, then this will mean that we can only assign to P a vector from the vector space that is attached to P, or the fiber that is attached to P. So if I use a different color here, I have to assign to P using S something on its own fiber. So let's say that this is a vector at P, and then that will allow pi to, which maps this entire fiber back to P, that means that this will become a round trip, and therefore it will be equal to the identity. I think last time in lecture 4 I called this the assigning to your own fiber property, something like that. Yeah. And so a holomorphic section is just a section where this map is a holomorphic map. And that's where you get into coordinate problems, because holomorphic in what coordinates? Well, that would be an inconsistent question unless the vector bundle itself was holomorphic, in which case it didn't matter which coordinates you defined it on, because they're all holomorphic and they're all compatible with each other. So that's why, sorry, this arrow is impaling this word. That's why we needed the vector bundle itself to be holomorphic. So then you have a holomorphic local frame field, pretty self-explanatory. Holomorphic local frame field, and it's just a local frame field S alpha, where S alpha is holomorphic. In a holomorphic local frame field, all of the components, not just S overall, but all of its component functions, so S alpha I, are all holomorphic, which makes it much nicer to do complex analysis with. So using holomorphic local frame fields, what we can do is, well, okay, so we've just defined all of this stuff. We have this holomorphic vector bundle, right? And so we would like the connection to preserve this structure. So there are other reasons why we want a holomorphic vector bundle. As I said, we can do complex analysis on the vector bundle consistently because of the fact that the transition maps are holomorphic, and so the coordinates are consistently holomorphic. But this will all be for naught if we don't have a connection that respects the holomorphic structure. So that's what we're going to build next. And so the first thing we're going to do is we're going to extend the Cauchy-Riemann equations to the holomorphic vector bundle. And this will come in the form of something called the canonical Dolbeault operator. This is an operator. Let's say that em pi is our vector bundle. So then the operator is called partial bar E for the vector bundle. That takes you from smooth sections on E to smooth sections on E times. So now instead of having a 1 form, we have a 0-1 form in the complex sense. So this comes from the anti-holomorphic what would I call it? The anti-holomorphic forms. I was going to call it the anti-holomorphic vector bundle, but that's not right. I think I should call it the anti-holomorphic cotangent bundle. Right? So these are so the analogy that we're trying to make here is that the Cauchy-Riemann equations kind of look like this, right? That's what would make something holomorphic, right? That's what makes a function holomorphic. So the analog of the d dz bar operator is this operator on the vector bundle. So in a specific holomorphic local frame field, let's say that our holomorphic local frame field is S uh, is L equal to E1 to EQ, and S is equal to S alpha E alpha. In that case, partial bar E of S is equal to partial bar of S alpha tensor E alpha. So there's another definition of a holomorphic section that comes from this operator. So this is kind of like a bootstrap definition. We defined it like forwards first, and now we're going to define it backwards from knowing what the result is. So we can also define a holomorphic section as partial bar ES is equal to 0. This means that S doesn't have any anti-holomorphic so no anti-holomorphic part, which is the same thing as what this equation is telling you, and this is a generalization of the CR equations, the Cauchy-Riemann equations. So with that, we are set to define something called a holomorphic connection. So so far, what we've done is we've taken, so remember all these decompositions that we did, right? So we had T star M O times C, and that was isomorphic to T star 1 0 M O plus, let me redo that, O plus T star 0 1 M. We also had D is equal to partial plus partial bar. Well, similar to these, we can also split our connection into two parts. We'll see how that works. So nabla, we can split it into what we're going to call nabla 1 0 and nabla 0 1. So the structure of these is very similar. Wow, what was that curly bracket? The structure of these is very similar to these, right? So where one of them is working on the holomorphic part, one of them is working on the anti-holomorphic part. And the reason I bring this up is because this structure of the tangent space, or the cotangent space, sorry, the cotangent bundle, is exactly why we can split this into two parts. Because what it's doing, so nabla 1 0 is taking us from smooth sections on E to omega 1 0 M times smooth sections on E. Yeah, here I wrote it correctly. So nabla 0 1 then takes us from smooth sections on E to omega 0 1 times smooth sections on E, right? So we basically split omega 1 of M into two parts, right? The holomorphic part and the anti-holomorphic part. And so what we're going to say is pretty simple. We're going to say that connection is holomorphic if nabla 0 1 is equal to the canonical Dolbeault operator on E. So this is what is going to make it so that in the coordinate decomposition, we get the Cauchy-Riemann equations coming up for each of the components. So this is slightly unsatisfying if we don't try to prove it. So we're going to prove it. So here we go. Let's say that, so proposition, if nabla is equal to nabla 1, 0 plus nabla 0, 1, and nabla 0, 1 specifically is equal to partial bar E, then nabla x of S is equal to 0. And this is what ensures the holomorphic structure. Sorry, I failed to mention that S has to be a holomorphic vector field. Yeah, holomorphic vector field. And X has to be an anti-holomorphic vector field. Okay, let's shorten that. Anti-holomorphic. Well, this one has to be a tangent vector field. You can see how this kind of looks like the Cauchy-Riemann equations as well, right? So this is what will tell us if that our holomorphic structure on the vector bundle is being satisfied. So let's start. So proof. First of all, we see that nabla x of S is equal to just nabla 0, 1 of S applied on X. Because nabla 1, 0 will be 0 because X is an anti-holomorphic vector field, right? So that's what allows us to just assume that this part doesn't exist. Because, because this is going to give us something on this side, which we don't have. Hello, editing Saif here again. So the explanation that I gave for why nabla 1, 0 was of S was equal to 0 was not very illuminating. So let's try that again, and let's see why that actually happened. So we had this nabla of x of S. So this was the covariant derivative, and we split it up like this. We were trying to do something of this sort: 1, 0 of S plus nabla x 0, 1 of S. Or, well, I was trying to say something like this, where we were applying it on here. And all of that is fine. The holomorphic vector field can still have a change in the anti-holomorphic direction. In fact, that's what we were looking for. We weren't trying to zero this part out. We were trying to zero this part out. So I got into thinking, what is it about X being anti-holomorphic that is important here? The reason that X has to be being anti-holomorphic zeroes this out is because, well, look at it this way. If we have the tangent bundle, then so this has to be a tangent vector field, remember? So if this is the tangent bundle, then remember that the complexified tangent bundle is isomorphic to T10 M, the holomorphic tangent bundle, direct sum with the anti-holomorphic tangent bundle, which looks like this. So that if we take a section on both sides, then we get something like that. Gamma of this, which is equal to or isomorphic to the gamma of T10 M plus gamma of T01 M. Which means that we can essentially, let's say that we have a vector field Z that's on the complexified tangent space, then that means that we can decompose this into Z10 and Z01. So this is the holomorphic part, and this is the anti-holomorphic part. Holo, anti-holo, right? But we said that X is an anti-holomorphic vector field, right? So what we really want to say here, so what I should correct, is that this should be x10, and this should be x01. And for an anti-holomorphic vector field, this is 0, meaning that x is equal to x01. Which means that if for x, this operator will zero out. This will be the zero operator because x doesn't have a holomorphic part. So it cannot track when we're trying to take the derivative of s along x, there are no holomorphic directions to take the derivatives of, which brings us to the interpretation of the two parts uh, of this operator. The first part tells you the change. Let me see if I can write that clearly. Change in holomorphic directions, and this is the change in anti-holomorphic directions. Now, if the vector field that you're using as an input is anti-holomorphic, well, there are no holomorphic directions to take a change in, and that's why this is 0. So it's a little subtle why this part is 0, but I thought it would be better to clarify why this is. It's not because the holomorphic, this would be the holomorphic derivative, right? It wouldn't make any sense for the holomorphic derivative of the holomorphic vector field to be 0. The reason it's 0 is because the input vector field that we're taking the derivative along doesn't change or doesn't have a component in those directions. So we're not taking the derivative in these directions at all. That's why it's 0. Which leaves us with this part, and then we continue our analysis on this part. So I'll have it go back to the recording now. Okay, so the next thing we have to do is we decompose this. We know what this is. This is partial bar E, right? So this is partial bar E of S. So then this is equal to partial bar E, canonical Dolbeault operator acting on S of X. But because of where did we leave it in the dust? Where is it? Okay, let me just write it again. Remember, partial bar E of S equals to 0 makes something a holomorphic vector field, and that's what this is. So this is true, which means that this, okay, how do we want to do this? Let's do it like that. This is then 0, right? So this is the 0 map. So the 0 map acting on X will just give us 0, which is exactly what we wanted. It shows that nabla X of S is indeed equal to 0. So that proves that whenever our connection has an anti-holomorphic part, which is the canonical Dolbeault operator, that it will imply that it is a connection that respects the holomorphic structure. And so we call those kind of connections holomorphic connections. So that is, so if nabla 0, 1 is equal to partial bar E, then our connection is a holomorphic connection. And it respects the holomorphic structure on the vector bundle. So now that we've defined holomorphic connections, we're going to look at these. The only thing that we have left to do is to look at these powerful topological invariants that we can define based on the connection and based on the curvature. And these are called Chern classes. So Chern classes have a really big theory associated with them called Chern-Weil theory. Chern-Weil theory. It's a shame we can't get too much into it because it's a little bit in the weeds. Um, I invite you to read up on it. You can read up on it in Chern, Chen, and Lam, and you can read up on it in other sources as well if you can, if you want to look it up. We're just going to talk about the summary of what the theory tells us, and then move on to defining the Chern classes so that we can use them later on when we're talking about Kähler manifolds and Calabi-Yau manifolds. So what are the Chern classes about? Well, fundamentally, they're about the twisting of the vector bundle. Twisting of the vector bundle. So remember in lecture 4 that we were talking about how the vector bundle is twisted. Let's say that that's U alpha. And then we have this diffeomorphism, phi alpha, that maps us to something called the local trivialization, which I call it a prism. You can also think of it as a bunch of uncooked spaghetti that's jutting out of the each of the local sections. And so this is called the local trivialization. And the fact that it's a diffeomorphism, what that tells us is that the transformation has to be smooth, right? And so there's a capacity for it to twist, but there isn't, you can't like break the spaghetti noodles, so to speak, right? So these Chern classes, they capture this idea of twisting through these invariant polynomials. Invariant polynomials. So where are the polynomials? I'll get to that in a second. They come from, so we have to talk about how the Chern classes are defined in order to kind of get an understanding of where these invariant polynomials are coming into play. So first, let's define something called the total Chern form. So that is C of E and nabla. So yeah, this is called the total Chern form. And it is equal to the determinant of, this is the next thing that I'm going to write is a matrix 1 plus omega, or I over 2 pi multiplied by omega. Forgot the factor there. So this is a polynomial, right? This is a polynomial. If you've taken some linear algebra, which you probably have, if you're taking complex differential geometry now, you know that the determinant is a polynomial. So we can expand this. Before we expand it, let me also explain why it's invariant, or what we mean by invariance. So invariance usually means invariant under some sort of transformation. In this case, the transformation is from GL QC, which is the general linear group on complex on the complex space, and it's q-dimensional. So this is the if you want to think about it in terms of matrices, which you can, these are the complex non-singular, that's the word I'm looking for, non-singular matrices. So any complex non-singular matrix, I mean one whose determinant is non-zero, that is a valid transformation. Valid transformation for what? Well, valid transformation for saying that omega, let's say that G is an element of this group, then it's the conjugation by this of the curvature form by this G is what is invariant, right? So this is invariant under this transformation. Invariant. And the polynomials that are invariant under this transformation create these topological invariants. And so the reasoning for that would require you to get into Chern-Weil theory, which we don't have time for, but that's the idea. And so this is that polynomial. And Now let us figure out where we get the Chern classes from, because this is not yet the Chern class. The total Chern form is a differential form, and from it we derive the Chern classes. So how do we get the Chern classes? So first we expand out CE nabla in terms of its terms. This is not an infinite series. It terminates. So we get 1 plus, we get something that we'll call C1 E nabla plus dot dot dot, there's C2 E nabla and so forth, and then we get at the end CQ E nabla. And then, so yeah, it's a finite polynomial and it comes from here, right? And so from here, so each of these is a form, and let's say we take the kth one of these. So for all k, ck of E nabla is a 2k form, right? And that comes from the fact that this is a 2 form. So you get that 2 being multiplied out, and the first one is the 0 form, right? So this is a 2k form, and this is called the kth total Chern form. This guy here. And from the kth total Chern form, we take the de Rham cohomology class. So here we go. Ck of E, this is the Chern class. Chern class. This is equal to, or this is defined by, the de Rham cohomology class of Ck E nabla. And this is an element of H2k dr, the 2kth de Rham cohomology class. That's the Chern class. So now we would like to, one thing that I want to make clear is that the fact that the Chern classes are de Rham cohomology classes is incidental. They're actually more fundamentally these things called elements of something called H2k of mz, where z is the integers, and these are called integral or integer cohomology classes. This is in a more broad context where you can define them fundamentally, but in the context of differential geometry, they turn out to be de Rham cohomology classes. Even though we're working in a complex vector bundle, they end up being de Rham cohomology classes. So that's an important thing to note. And there are real versions of the Chern class. They're called the, let me see if I can write this first time correctly, Pointer-Yagin classes. And those are elements of H4k mz. But we definitely don't have time to talk about those, but maybe you'd want to know what they are. So therefore I that's why I talked about them. So we specifically are interested in the first Chern class, which is defined by C1E. This is just a relationship. You can find this in linear algebra. The first term in the determinant will turn out to be the trace. So you get that this is equal to the cohomology class that contains the particular form I over 2 pi trace of omega. So that's the first Chern class. It's more important for us than all the other classes. That's why I highlight it. And we can interpret it if we use the integral. So the integral of C1e, remember, it's a form. So we can just take any form in this class. So this is a representative of this equivalence class. And we integrate it over a two-dimensional surface, a two-chain, let's say. And so if we do that, we get an integer. This has a lot to do with the fact that it's an integer homology class or cohomology class. But this integer has the interpretation of the number of twists of E around sigma 2, the surface, right? How many times it coils around sigma 2. And that's also, by the way, why we have this factor out in front. It's to normalize this and make sure it actually turns out to be an integer, because otherwise it would have like minus 2 pi I, or yeah, a minus 2 pi I, something like that, multiplied out in front, which we are dividing out because by that normalization, right? So, right. So that is the first Chern class. So now we're going to talk about some properties. We're going to end now on talking about some of the things that make the first Chern class special. So some special properties. Number one, C1e is independent of nabla. It's independent of nabla because of the fact, well, it's because of this is a central result of Chern-Weil theory. So you'd have to like go into the theory in order to give a full explanation of it. But Chern-Weil theory, one of its big results is that C1e, even though it depends loosely on C1e nabla, the nabla dependence actually drops out of this cohomology class, and so they become particularly easily computable because we can use the most convenient nabla to compute the first cohomology class, and it will be the same for every connection. So number two is additivity. If L1 and L2 are two line bundles, line bundles are also important because they come up in something called divisor theory. But I don't really know divisor theory, but that's one of the motivations for talking about line bundles, and they're very important in classifying holomorphic vector bundles. So if that rings any bells for anyone, then I'll just put that in there. But additivity is the idea that C1 of L1 tensored L2 is equal to C1 of L1 plus C1 of L2. This makes them nice to work with. This also gives them something called a logarithmic character. This is not a technical term. I'm just this is just me being a little vague here. The fact that they turn something that's a product into something that's a sum kind of makes them work a little bit like a logarithm. So you can think of them as like some sort of logarithmic property on the bundles. Okay, so number three is going to property number three is going to force us to, how do I want to say this? To define property number three, we're going to need a new kind of bundle called a dual bundle. I was contemplating talking about dual bundles in lecture 4 when we were talking about bundles, but I thought we're not going to need them until right now, so might as well define them right now. They're not very difficult. If E is a bundle by abusive notation, this is the bundle space, but we'll call it the bundle. If E is a bundle, then E star is the dual bundle. if um, yeah, if EP, so EP star, the fibers, is equal to the fiber of this bundle, the dual space of the fiber of this bundle. So if that's if the bundle has a vector space V, then the dual bundle's vector space is V star. That's basically it. And then this is called the dual bundle. So it's a bundle whose fibers are the dual spaces of the regular bundle. So we can say for a dual bundle that C1 of E star is equal to the negative of C1 of E. So in some sense, the twisting of the dual bundle is in the opposite direction of the twisting of the regular bundle. That's interesting. This is actually a consistency condition with the previous with this previous property. And the reason for that is that if we look at this, if we talk about C1 of L times L star, L times L star is actually equal to the trivial bundle. So the trivial bundle is the bundle that has no twist. It's equal to M times CQ. It's equal to its own local trivialization. So you could call that a global trivialization or globally trivial. It's literally just the prism of CQ being projected out of the manifold, right? It's just that block that I've been drawing in as a vector bundle. So if we look at this, then this is equal to C1 of L. For reasons that's hard to get into right now, C1 of T is equal to 0. So this is equal to C1 of L plus C1 of L star. And so if this is equal, so then this has to be equal to 0, right? 0. So then that implies that C1 of L plus C1 of L star is equal to 0, which implies that C1 of L star is equal to C1 of L. Yeah. So that implies, because this has to be true for line bundles, it also has to be true, like for the Chern classes to be consistent, this also has to be true for the general bundles as well. We're kind of like saying that this will imply this, right? This will make sure that this condition is true. So that's property number 3. So these are some of the nice properties that we get for the first Chern class. And that will do it for our lecture on connections, curvature, and Chern classes. So we're done with Chern classes now. So let's do a brief recap of what we did. I'm going to try to make this one actually brief. So we started off talking about the fact that complex connections, they need to satisfy J of nabla x s is equal to nabla x of J of s. But then we also needed to define something called the holomorphic vector bundle. We also defined a holomorphic section. We defined a holomorphic local frame field. Then we defined the canonical Dolbeau operator. If I can spell canonical Dolbeau operator, partial bar E, and we use that to define a holomorphic connection. one for which if nabla is equal to nabla 1, 0 plus nabla 0, 1, then nabla 0, 1 is equal to partial bar E. And we showed that this is equivalent to the holomorphic of the connection to respect the holomorphic structure. So once we did that, we moved on to Chern classes. So Chern classes. We showed that they're something to do with the number of twists of the vector bundle. And we looked at their definition, which is that ck of E is equal to the class of ck E nabla, which are elements of H2K dr of M, where M is the base manifold. And this is from this series 1 plus C1 E nabla. You get the picture, dot, dot, dot. And this came from this expression, determinant of 1 plus I over 2 pi omega. Where this thing was called the total Chern form. And then we looked at three properties. I'm not going to list them again. We just went through them. Three properties of C1 of E. And that'll do it. So that is it for lecture 9. So next time, it's exciting. Next time we're going to do the last prerequisite for talking about Kähler manifolds. We're going to do metrics. Specifically, we're going to look at Hermitian manifolds. Then we're going to look at metric compatible connections. And if we want to like marry that with the complex analysis that we've been doing so far, we're going to get a new kind of connection called the Chern connection. So that's what we're going to do next time. So see you next time on metrics and metric compatible connections. Goodbye, everyone.